Hello, this is the lecture on linearization of the course Controle em Espaço de Estados. To follow this topic, if you are able to read Portuguese, you can read chapter 7 of the book Controle no Espaço de Estados by João Miranda Lemos, from pages 273 up to 302. So, the objective is twofold. First, to provide a tool to study the stability of equilibrium points based on linearization about that point. And the second is to provide a tool to design controllers for nonlinear systems based on linearization about equilibrium points. So consider an equilibrium point of the dynamic system x naught equal to f of x. So I'm assuming that f is a vector field which is smooth enough so that the state model is well behaved. So the solution is unique once you specify the initial condition. There are no chaos phenomena, and there are no sensitivity to initial conditions. So I call x bar an equilibrium of this point, of this system. And so f of x bar is equal to 0. That's the definition of x bar being an equilibrium point of x dot equal to f of x. Suppose that you have a state x which is close to the equilibrium. Not at equilibrium, because if x is at equilibrium, it will remain at equilibrium, but close. So at a position which is given by x bar plus delta x. Well, delta x is an increment of the state around the equilibrium that I assume that remains small. And first, we are going to obtain an approximate model for delta x. So we start by writing the nonlinear state model x dot equal to f of x, and by remembering that x is given by x bar plus delta x, so the equilibrium plus the increment. And we replace this wherever x appears. Now, the derivative of the sum x bar plus delta x is the sum of the derivatives. And we are going to approximate f of x bar plus delta x by the first two terms of the Taylor expansion of f of x bar plus delta x around x bar. Now we observe that the derivative with respect to time of x bar is 0 by definition of equilibrium point. And furthermore, f of x bar is also 0 because x bar verifies this equation with f of x equal to 0. So the state equation remains the derivative of the increment is equal up to second order terms, which I represent by this undulated equal sign, is equal to a matrix given by the derivatives of f with respect to x. This is the Jacobian matrix computed for x equal to the equilibrium times delta x. So this matrix is a matrix made of constants because the Jacobian matrix is a function of x, but then you made x equal to x of x bar, which is concrete as a concrete value. So this is nothing more than a time invariant homogeneous system that is verified by delta x. And this is what is written in this slide of conclusion. So if you have a nonlinear system of which x bar is an equilibrium point, then the increments delta x about this equilibrium point verify this homogeneous equation with the matrix A given by the Jacobian matrix of f with respect to x computed at the equilibrium point. Let's see one example. Suppose that we have this system this is a second order system, and it's not difficult to see that it has two equilibrium points at -1, and 1. And you can easily interpret these equilibrium points in a geometrical term, as shown in this slide. Now, remember that F1 is x1 minus x2, F2 is 1 minus x1, x2. So if you compute the Jacobian matrix, you just get this matrix here, where in the first line you have 1 minus 1, and in the second line you have minus x2 minus x1. Now, depending on the equilibrium point that you consider, you are going to have a different linearized model. So for the point -1, you replace x1 and x2 by the coordinates of this equilibrium point, and you get this matrix, this dynamic matrix of the linearization about the point -1, and then you can do the same for point 1. So this example illustrates in a very clear way that you can have different equilibrium points for nonlinear systems, and to which point you will have a linearization. So it's pointless to speak about the linearization of a system. You only speak of linearization of the system around a given equilibrium point. If you change the equilibrium point, you will change the linearized model. Now, suppose that your system has an input. So your f is a function of x and u, and you can, in this case, you must define equilibrium value for the manipulated variable u, that I call u bar, and then if I have deviations of u with respect to u bar, I call these deviations delta u of t. Then the system responds with state x, which is a sum of the response of the system with respect to u bar plus some delta x. Now, if the system is time invariant, the only equilibrium points are time invariant. So u bar is constant, and x bar is constant also. And you can also do a similar reasoning to obtain for the increments the state model that you can see here at the bottom of the slide, where A is the matrix of first derivatives with respect to x, of f with respect to x, and B is the matrix or vector, depending on how many inputs you have, of f with respect to u, but both computed at equilibrium values for x and u. If u is not constant, if u bar is not constant, then you can still do the linearization, but an extra term appears in the linearized model. This is a situation that for the moment we are not going to consider, but you might want to consider that situation when you think about this problem. Now, if you consider a nonlinear system with an equilibrium point and linearization about the equilibrium point, you do the linearization, And you might say, well, the behavior of the increments that satisfy the nonlinear equations and the increments that satisfy the linear equation, they must be close to each other, provided that they are not very big. Actually, this is not always so. I mean, sometimes the nonlinear system around an equilibrium point in the linearized system, they have very quite different properties. One example is controllability. Suppose that you have this nonlinear system. You see that the equation for x1 is linear, but the equation for x2 is nonlinear. You have a power 3 of x1. Now, if you linearize, you get this. And it's easy to see that if you compute the controllability matrix for this pair A, B, that corresponds to the linearized model, the rank of the controllability matrix is 1. That is to say, there are points in state space of delta x that you are not able to attain if you are operating the linearized model. But it's not proven in the slide, but it would not be difficult to prove that in the nonlinear system, you can attain all points around the equilibrium point 0, 0. So what is the miracle? The miracle is that this cube has disappeared in the linearization, and this is this nonlinear term that allows you to influence x2 when you manipulate x1 through u. And otherwise, when you linearize, this term here disappears, and you are no longer able for the linear system to make u to influence the state variable x2. So this is an example in which controllability properties of a nonlinear system and a linearization can be quite different. So you should be careful. You might also wonder whether it is possible to study stability properties of a nonlinear, of the equilibrium of a nonlinear system by studying the stability properties of its linearized version. Actually, this can be done, but with limitations. Before we proceed, let's define what we mean by stability. There are many ways to define stability, and we are going to use the concept of stability in Lyapunov sense. We say to define stability in Lyapunov sense, we use a definition, which is a kind of game that I play with someone, let's call him Peter. And what is the idea? The idea is the following. Suppose that I want, or Peter tells me, I want the state x of t to be within the ball of radius, let's call it 5. If the equilibrium is stable in the Lyapunov sense, then I should be able to find a smaller ball of radius, let's say 1, such that if the initial conditions start within this ball for all possible initial conditions, they will stay within the ball for all time. The state will stay for all time within the ball of radius 5. Now Peter says, well, let's make it a little bit more difficult. So instead of keeping x of t inside of a ball of radius 5, let's keep it into a ball of radius inside a ball of radius 2. So if the equilibrium point is stable, I should be able to restrain the set of initial conditions, finding perhaps a smaller ball, such that initial conditions now leads to states x of t that remain within the ball of radius 2. And for a stable equilibrium point, this should work. We could go on for any ratio, any radius that Peter specifies, no matter how small it is. So, in general terms, we say that the state of equilibrium is said to be stable in the sense of Lyapunov, and here we are considering the equilibrium to be the origin of state space. If for any capital R which is strictly bigger than 0, there exists a smaller r which is strictly bigger than 0, such that if the norm of the initial conditions are smaller than r, then the norm of the state xt will be smaller than capital R for all t. And so this must happen for all possible capital R. So let's think about this question to understand a little bit better this definition. The van der Pol oscillation is given by these two equations. And from one side, it's very easy to see that the origin x1 equal to 0 and x2 equal to 0 is an equilibrium point. So if you make x1 equal to 0, x2 equal to 0, both derivatives vanish. So 0, 0 is an equilibrium point. Furthermore, we have seen in another chapter that preceded this one that the van der Pol equation oscillator has a limit cycle that encircles or is around the origin. So this means that there is a closed trajectory that you can see here in the plot, such that if you start over this trajectory, you will remain on it, and this gives rise to a periodic solution. Now, if you start at equilibrium, of course you stay at equilibrium. But if you start a little bit away from the equilibrium, you will spiral, getting closer and closer to the equilibrium, to the limit cycle. And so all trajectories that start close to the equilibrium will be bounded in the sense that they don't go away from the region encircled by the limit cycle. Now, is the origin stable in the sense of Lyapunov? Think a little bit. Actually not, because if your R is very, very big, such that it contains a limit cycle, then provided that you that you select a circle of a radius small r, which is inside unit circle, then you will all trajectories will be inside unit circle, and since the unit circle is inside the big circle, then you will be inside the big circle. But stability demands that you are able to do this, to stay in the big circle of radius capital R for all possibles of capital R. So if you select a circle of radius capital R, which is inside unit circle, it's impossible to restrain the set of initial conditions such that you remain inside it. So the origin is unstable point in the sense of Lyapunov. It's not stable. Well, this example is interesting because our intuitive notion of stability is associated to variables that go to infinity. Now, the states in this case do not go to infinity because they are bounded by the unit circle, but the equilibrium 0, 0 is unstable because of the definition that we are using. Now, another notion is asymptotic stability. We say that the equilibrium point is asymptotically stable if it is stable, and if furthermore there is a circle, a value, a value for small r, such that if the initial conditions are within this small ball, then xt goes to 0 when t goes to infinity. That is to say, in asymptotic stability, you don't ask just for being stable, but you demand that your state returns to the equilibrium point. An important difference is between local stability and global stability. If asymptotic stability holds for any initial point in the state space, then the equilibrium is said to be globally asymptotically stable. Otherwise, it's just locally asymptotically stable. Now, what is the relation between the stability of a nonlinear system around the state of equilibrium and the linearized model around this same equilibrium point? It's very simple. You compute the eigenvalues of the linearized system. And if the linearized system is asymptotically stable, that is to say, if all its eigenvalues have negative real part, then the equilibrium point of the nonlinear system is also asymptotically stable. If you have at least one eigenvalue with a positive real part, then the nonlinear system equilibrium will be unstable. Now suppose that your eigenvalues have either a negative real part, but some have a zero real part. So you have a pole at the origin, or you have two eigenvalues over the imaginary axis. In this case, you can't state anything about the stability of the nonlinear system. And this is because, in this case, the linearized model is at the boundary of stability, and the nonlinear terms will make the balance go to either stability or to instability. Let me give you one example. We have these two nonlinear systems, system A and system B, and you can see that system A is unstable and system B is asymptotically stable. You can see, you can look at the trajectories of the asymptotically stable system spiraling towards the point 0, 0. Now, both these systems have the same linearization around the origin, and this is given by this linearized model. And if you compute the eigenvalues, you get a pair of imaginary values. So this is the situation in which, from the linearized system, you cannot say anything about the nonlinear system. Indeed, in this case, you had two different nonlinear systems, one asymptotically stable and the other unstable. Just for curiosity, how could we generate this model? Well, use polar coordinates and then make a change to rectangular coordinates. Now, let's use this result to analyze a situation related to HIV-1 virus infection. So HIV-1 virus is what we call a retrovirus, and I will explain you in a moment how is it made. It has a capsule, and this capsule has a number of proteins, in particular this GP120, that are used to connect the virus to the walls of cells that it infects. And inside, what you have? You have the genome of the virus codified in RNA. You have a number of enzymes. You have reverse transcriptase, you have integrase, and you have protease. Now, how does it work? So you can see here a sequence of pictures representing the virus in one becoming attached to the walls of the cell. So the cell is blue part here. And this is done through the GP120. Then the virus injects inside the cell its RNA and together with enzymes. And reverse transcriptase is able to produce virus DNA from the RNA. This is why this is called a retrovirus. So it refers to the possibility of this virus to reconstruct DNA from RNA. And so you get the DNA of the virus, which is inserted using integrase in the DNA chain of the cell. Now, these cells are not general cells. They are cells of the immunitary system. The immunitary system is the system that defends the body against infections. Basically, it has two types of cells. I mean, it's very complicated. You can read a book on immunology, but in a simplistic way, you have cells that are like secret agents. They try to differentiate what is part of the body and what is not part of the body, the self and the non-self parts of the body. And once you detect something which is not part of the body, then you have the second type of immunitary cells. They are kind of soldiers that come and try to neutralize this part. And since you are modifying the RNA and the DNA of the immunitary cells, what you are saying is that you are destroying the capability of the immunitary system to defend the body against infections, for instance. So in HIV-1, you don't die of HIV-1 infection. You die because the body is no longer able to be defended from other infectious agents. So you die of tuberculosis or you die of any other disease. Now, once the cell is, the DNA of the cell is contaminated, instead of producing the elements that will allow the cell to replicate correctly, it starts producing parts of proteins and parts of RNA that are assembled by protease and produce new virus particles. So a cell produces new virus particles. That's the way HIV-1 infection replicates. Now, how can we model this using a state model? So this network here represents the process that I have just referred. And look at the equations. We have a state made of three variables. T, capital T, is the concentration of healthy cells of the immunitary system. Actually, it is T CD4 plus cells. T star is the concentration of infected cells, and V is the concentration of virus particles, the so-called virions. And we are assuming that the rate of production of new cells has a constant term, which I represent by this term S. Then it has a death term, so there is a death rate, and D is the death rate in the absence of infection. And then T also decreases because you have healthy cells being transformed into infected cells by the action of virus. So this combination is represented by this beta, which is a constant, times TV. Now, if you look at the equation for the infected cells, what disappears in the healthy cells will appear in the infected cells due to the infection, and then you have a death term similar to the D, but now I call it mu2, the rate of death of infected cells. And the rate of production of new virus is proportional to the number of infected cells. And then you have a term, let's call it death of the virus, although with an abuse of language, because the virus is not a living body. It's a neutralization of virus due to several reasons. Now, if you simulate these equations, what you see is that something that appears. This is a typical simulation of your body responding to an infection. So initially, the number of healthy cells is quite high, close to 1,000 cells per cubic millimeter. And you have no infected cells, and you have a V which is very, very small. Okay, so 1 or 2. It should not be 0, because if it was 0, then the T cells will evolve in a different way, and the infected cells and the virions will remain at 0, according to the equations. Now, what happens is that in the first few weeks, you see, this is time in days. In this case, for the parameters, after say first 50 days, so about 4 weeks, 8 weeks to 2 months, is what you have this spike of infection that then decreases, and we go to the equilibrium, and the healthy cells decrease, then recover a little bit, and they stay like this. What happens usually is that after a long period of time, say 2 years, now with treatment is quite different. It can be even 10 or 20 years. The number of healthy cells vanishes, and the infected cells and the virions grow very fast, and the person dies of the so-called AIDS syndrome. But this is, of course, not represented in this simple model. One thing that you see here is that you are going to an equilibrium. So let's speak about equilibrium points. The equilibrium points is when you vanish the derivatives. So you have to solve these equations with respect to T, T star, and V. And they are algebraic equations. So with a little bit of algebra, you can see that you have 2 equilibrium points. One that corresponds to the person that is not infected is given, I call it equilibrium 1, and in the equilibrium 1, both the infected cells and the concentration of virions is 0. Then we have the infected person in equilibrium, and in this case, all the 3 variables go to a non-zero equilibrium. Now, what about the stability of these equilibrium points? So let's start by computing the Jacobian matrix of the equations, which is the result is here. You are invited to do the computations by your own, and you can use, for instance, these parameters. And if you compute the Jacobian matrix using these parameters for the equilibrium point corresponding to the known infection, you get this matrix, you compute the eigenvalues, and surprise, you see that else is unstable because there is an eigenvalue with a positive real value. Okay? There is an old joke that says that else is a transient state that is not that does not announce anything good. You can only go worse. And the fact that it is a transient is associated to the fact that it's unstable. So how is it unstable? Because if you add some virus, so you do a small perturbation, you are moved away from this equilibrium. Let's see what happens to the other equilibrium corresponding to the infection. In this case, you have still 3 poles, and the real parts of these eigenvalues are all negative. So the infection is stable. Even if there is some fluctuation in the number of virus or infected cells with respect to the model, then you always return to the equilibrium because it's stable. It's actually asymptotic stable around it. Now, you can do a plot in state space starting, computing the state trajectories and starting around different initial conditions. And you can see here where I'm pointing. This is the healthy state, which is unstable. It's a kind of saddle point. And you can also see here the equation, the point that corresponds to the equilibrium point of infection. Another interesting thing to note in this example is that things appear to be in a plane, okay, in a tilted plane. So probably if you do a reasonable change of variables, you will be able to develop a model with just 2 variables. And actually, this is true, but it's another story. Now, let's say a little bit about control. So we have studied stability. Now, what about controller design? So let's see how are things organized. Suppose that you have a nonlinear process with a manipulated variable u and an output y. And u can have wide changes, and y also wide changes. Okay? And if you subtract u bar and y bar, then you get increments. So if you subtract y bar from y, you get delta y, and you feed it back, and you have a controller, which I call an incremental controller, that works with an incremental reference delta r. So delta r is a reference for delta y. And this incremental controller produces some incremental value of the control that you add to the equilibrium value of the control to produce u. Suppose that you are, if you have a system in which you are injecting, you have a valve. So u is the position of a valve. Well, a valve is either open or fully closed. So usually codify fully open 100%, fully closed 0%, and in between, say u equal to 50, it's half open. You don't have a negative opening of the valve. That's physically, that's impossible. But so how come that your controller gives you negative values for the manipulated variable? This is because what your controller does is to produce the increments around the equilibrium point. So suppose that, for instance, your equilibrium point is u bar equal to 50%, and your delta u is minus 5%. So this means that the u that you are applying to the process is 50 minus 5, which is 45, still positive. So what is negative is the increment, but since the increment is added by the equilibrium points, there is no saturation at 0. And the same thing here, okay? So one thing also that you should notice is that usually this y bar is you see it incorporated or added to delta R to build the full reference that compares. And if you add delta R with Y bar, it's a reference that compares to Y, to the full signal Y. And furthermore, this U bar, either you can force it, or you can have the integral action, the famous integral action that you should embed in many controllers that generates this U bar. Remember that integral action works in the long run, and it's a kind of constant that is adjusted so that in equilibrium everything is as it should. So let me show you one example to illustrate this point. And this example is related to the control of depth of anesthesia in patients subject to surgery. Again, you can find it in the book on control no espaço de estados in these pages, in the indicated pages. You have several variables to define the anesthesia. And one important variable is the loss of consciousness that you can measure using different signals. I'm using the B signal, well, let's say it's some magic way. It's not magic, of course, but it's something that it's produced by a sensor or sensitive equipment, sensor equipment, that produces a signal between an index between 0 and 100. And 0 means deep coma, and 100% for this means that the person is fully awake. And below, you see the rate of infusion of some drug with the serum. You can see here the computer control. Actually, this is the chirurgical amphitheatrum, and these are the pumps that are used to generate these signals. Okay, so your computer gives orders to those pumps that then they are connected to the patient that you don't see in the picture. Now you can see some dashed lines here, both in the output signal B's and in the manipulated variable signal. And these dashed lines correspond to the equilibrium values. So we are using a Y bar equals to 50 and U bar equals to 100 micrograms per kilogram of patient per minute. That's the flow, units of flow. So what the controller is computing, the controller is reading the deviations of the B signal with respect to this equilibrium and does some computation and then computes some this increment. So in this case, for instance, at this time, you have a negative increment. That is to say, you are applying less than the equilibrium, but the delta U is negative. And in this way, you are able to regulate this level. Now, you can, in the previous example, you can, we were just keeping a variable close to some value. That's the so-called regulation problem. But in some cases, you can change the set point. You want to change the set point. And in this case, you can have different controllers that match different equilibrium points defined by these different levels of the output. And what you do, for instance, for controller C1, you multiply it by the weight, which is close to 1 for small values of the output variable, and 0 for high values of the output variable, y. Okay? So this controller will be active only when y is small. And similar, C2 will be active for a mid-range of the values of the output, and C3 for high range. If you are, say, between low range values and mid range, then you have a linear combination of the output of both these controllers applied to the system. So these weights are a kind of glue that stack together the different controllers. It's like having patches. So you have a blanket made of patches. Each patch corresponds to a controller. And then you have to sew the patches together, which is done by these weights. This is a technique known as gain scheduling, which is much widely used in industrial applications, not only in the process industry, but for instance, in controlling aircraft, where you patch different controllers corresponding to the different flight conditions. And this is an important practical thing. So in this lecture, the main topics were three. First, we understood how to linearize the dynamics of a nonlinear system around an equilibrium point. And this depends on the equilibrium point that you consider. The second thing that we have learned was to infer the stability properties of a given equilibrium point from the linearized system. This can only be done when you don't have eigenvalues of the linearized system over the imaginary axis. And the third thing is remind that you can use all the techniques that you have studied before to design linear controllers by applying them to the linearized model and then adding and subtracting in a convenient way the equilibrium points. Thank you very much for your attention, and we stop here.